Hello, physics students. Here is your concept development practice page 5.3. So we're continuing to work with vectors and the parallelogram rule. We want to look at what kind of speed or resultant speed our objects have. So number 1 says, when two vectors A and B are at an angle to each other, they add to produce the resultant C by the parallelogram rule. Note that C is the diagonal of a parallelogram where A and B are adjacent sides. Resultant C is shown in the first two diagrams, A and B. So here's component A, here's component B, here's our resultant. Here's our component A, right? Our, if you will, vertical component. Here's our component B, which is kind of our horizontal component, and here's our resultant C. Construct the resultant C in diagrams C and D. Note that in diagram D, you form a rectangle, a special case of a parallelogram. So just like the other ones, right, our resultant is going to go from where our two vectors originate to kind of the opposite side. So here is my vector C, which is my resultant. For this next one, I have to draw those parallel ones first, right? So here's my first parallel. Okay. Here's my second parallel. And then my resultant goes across. So there's my resultant C. Okay. So, number 2, below we see a top view of an airplane being blown off course by wind in various directions. Right? So this is the velocity of my airplane. And here we see the velocities of the wind. Use the parallelogram rule to show the resulting speed and direction of travel for each case. So what they're asking me to do is construct these parallelograms. So here's my first parallelogram. And my resultant velocity, combining the airplane's forward motion and the wind that's blowing it, here's the path and the velocity that this plane would actually be taking. So in our second one, right, here's my parallel line to my forward, my plane velocity. Here's my parallel line to my wind velocity. And the resultant velocity of these two, of the plane's forward velocity and the wind that is blowing it, is this resultant vector that I just put in. Okay. So here's my next one, plane C. Right, here is my parallel to the plane's forward motion. And here's my parallel to the wind's motion. And my resultant velocity, again, goes from kind of where they meet to that opposite corner. So there's my resultant velocity and direction. Now, my last one here, right? Here's my parallel for my wind. Here's my parallel for my plane. And here's my resultant velocity. Okay. Now, it asks, in which case does the airplane travel fastest across the ground? And basically, fastest is going to mean the longest vector. So if I'm not sure, if you can't just tell by looking at it, right, I could kind of measure them. So I have about 4 centimeters there. A little bit more than 4.5 centimeters there. Only about 3 centimeters there. This is the one I wasn't sure about. Right? That one's almost 5 centimeters. So the fastest one is D because the vector is longest. And the slowest one, remember, was letter C because that one was only about 3 centimeters. Okay, so we know it's the fastest. We don't have to do math to figure it out. We can just look at the pictures that we drew. Whichever one has the longest resultant vector is moving the fastest. And the one with the shortest resultant vector is moving the slowest. So number 3. To the right, we see the top views of 3 motorboats crossing a river. All have the same speed relative to the water and all experience the same water flow. Construct resultant vectors showing the speed and direction of the boats. Okay, so we're doing the same thing here, right? So here's my first one. Okay, so there's my parallel to my kind of boat motion. Here's my parallel to my river motion. And the resultant of this is right there. Okay, so my next one, here's my boat motion. So here's my parallel to my boat motion. Here's the river motion. So here's my parallel to my river motion. And here's my resultant velocity and path that my boat would take. And my last one, right? Here's my stream or river velocity. Here is my boat velocity. And my resultant velocity. Okay, so there are my 3 parallelograms done. Now, the first question. Which boat takes the shortest path to the opposite shore? So shortest path also means the shortest vector. And again, if I'm not 100% sure based on my drawing, I always could measure it. Okay, right? So I have about 2 centimeters here. Here I have, about 2.5 centimeters. And on this one, I have about 3 centimeters. So the shortest path to the opposite side is going to be boat A. Which path boat reaches the opposite shore first? Right? That's going to mean that it's moving, okay, kind of fairly quickly. And it's going to get there. So that's going to be boat B. And which boat provides the fastest ride? The largest velocity, right, is letter C. So shortest path, because the length is the shortest. Okay, opposite shore first, okay, again, because of the length here. And then fastest ride, because this is the longest vector. So velocity vectors and components. Again, we're drawing the resultants of these four sets. So we're going to make our parallelogram. And then draw our resultant. Hopefully you're getting pretty good at this. Right, so here's our parallelogram. Here's our parallelogram. And here's our resultant. Here's our parallel. Here's our parallel to our horizontal. And then here's our resultant. And then this last one again. Here's my parallel. Okay, and here is my parallel. And my resultant. All right, so there's those. Right, so here's my vertical component horizontal of this resultant, vertical horizontal of this resultant, vertical horizontal of this resultant, okay, vertical horizontal of this resultant. 2. Draw the horizontal and vertical components of the four vectors below. So we're doing a parallelogram, but we're trying to find those vertical and horizontal components this time. So here's my vertical component. Here is my horizontal component for that first one. Second one, here are my two vertical parts for my parallelogram. Here's my second horizontal part. So here's the vertical component, and here is the horizontal component. All right, the next one, right? It's my horizontal component. It's one of my verticals. Here's my other vertical. So here's my vertical component, and here's my horizontal component. And this next one, and here's one of my verticals. Here's my other vertical. One horizontal is there. Here's my second horizontal. And then again, here is my vertical component. And here is my horizontal component. Sorry. So number 3, Nellie Newton tosses the ball along the dashed path. The velocity vector, complete with its horizontal and vertical components, is shown at position A. Carefully sketch the appropriate components for positions B and C. So this means that we have to understand some things about motion. Remember, our horizontal component of velocity stays the same. So this is constant. It's unchanging. So at each of these positions, this horizontal component will be the same. So I'm going to kind of measure it here to see about how long it is. and I'd say it's 1.5 centimeters. So up here, I'm going to draw a 1.5 centimeters component. And right here, I'm going to draw a 1.5 centimeters component. And that's my horizontal component. It's constant, it's unchanging. When we assume, again, we're always assuming we don't have the effect of air resistance. Now, the vertical component, remember that's affected by gravity. Right? Gravity is acting at 10 meters per second squared downward. So up here, where remember now this is a special circumstance, right, where we're at the top of our path. What's true of the vertical component of our acceleration or of our velocity at the top of our path? Remember, our vertical is 0, okay? So there is no vertical component at B. Now, at C, we can figure out what it is here. We don't have to have math because remember, notice we're at that same height. And remember, when we're at the same height, we're going to have the same vertical component of our velocity. So it's just going to be acting in a different direction, right? So here I can measure this one. And it's about 2.5 centimeters. So that means that this component here is also going to be about 2.5 centimeters, but it's going to be acting downward now. Okay, so here's our vertical, here's our horizontal, here's our vertical. And notice that because these are at the same height, both components are the same. So we've done the appropriate components. So letter A asks us, since there is no acceleration in the horizontal direction, how does the horizontal component of velocity compare for positions A, B, and C? And it's the same, okay? Because there is no, acceleration, our velocity in the horizontal direction is constant or unchanging. B, what is the value of the vertical component of velocity in position B? It's 0, right? Because that's when that ball that we've thrown up is momentarily not moving at the very top of its path. So it would be 0 meters per second. C, how does the vertical component of velocity at position C compare with that of position A? Notice they're equal in magnitude, but they're opposite in direction. So they are equal in magnitude or size, but they are opposite in direction. Okay? So they're equal in magnitude or size, they're the same length, but they're acting in opposite directions. Here the ball is moving upwards, here the ball is moving downwards, or yep, it is a ball. All right? So, again, these concepts are pretty important for you to understand. It makes answering some questions easier because you can answer them without any math. Have a great day. I'll talk to you tomorrow.